Welcome to the Deep Dive, the show where we take a stack of sources, in this case some incredibly insightful architectural thinking on data systems, and deliver the critical knowledge you need to navigate the information age.
Today, our listener, the learner, has tasked us with exploring one of the most fundamental principles in engineering, accepting failure.
Yeah, that's really the core of it, isn't it?
It is. When you build these large-scale data applications, the question isn't if something will go wrong, but, when it will go wrong.
Absolutely. The whole deep dive today is about understanding those inevitable faults and then the really sophisticated, clever strategies that engineers have come up with to overcome them.
Right, because when you're building systems that handle these immense amounts of data systems that are, let's be honest, running the modern economy, you have to design them against the universe's natural tendency towards chaos.
I love that framing.
Yeah.
It reminds me of what the physicist Richard Feynman said. He put it perfectly. For a successful technology, reality must take precedence over public relations, for nature cannot be fooled.
And the reality of building distributed data systems is that at the component level, they are inherently unreliable, just fundamentally.
So the goal is to make them reliable despite that.
Exactly. The system as a whole has to be reliable, even though its parts are not.
Okay, so our mission today is to really unpack this reality for you. We're going to be focusing specifically on what are called data-intensive applications.
And that's a really key distinction to make right up top.
It is. The primary challenge here isn't a bottleneck in CPU speed. It's not compute cycles.
No, it's not a CPU-bound problem. It's about the data itself.
The sheer volume of the data, its complexity, or just the rapid rate of change of that data. We're talking about information infrastructure.
And to manage all that chaos, engineers really focus on three foundational goals.
The big three.
The big three. First, reliability. The system has to continue working correctly, delivering what you expect, even when things inevitably go wrong.
Okay, that makes sense. What's number two?
Second is scalability. So the system has to maintain its performance, its throughput, even as the load, the data volume, the number of transactions just dramatically increases.
It has to grow gracefully.
Exactly. And third, maintainability. The system should stay easy for engineers to operate and modify. It has to be productive, even as the teams and the complexity grow over time.
Okay, and I think we need to get really precise about the language here. When we talk about things going wrong, we have to distinguish between a fault and a failure. They sound similar, but they're not.
A critical distinction. A fault is when one component deviates from its specification.
Like a hard drive dying.
A hard drive dying, a network packet being dropped, that's a fault. A failure is the consequence. It's when the system as a whole stops providing the service you expect it to.
Or worse, corrupts data.
Or worse. So the whole game, really, is designing systems that can tolerate faults without ever experiencing a failure.
So to do that, you have to know your enemy. What are the main categories of faults, the incidents that engineers are constantly up against?
They really fall into three broad categories. The first one is the most tangible, hardware faults.
These are the classics, the things you can, physically touch.
Exactly. Your disk drive crashes, a stick of RAM flips a bit, the power supply just gives up.
The good news here, I guess, is that these are usually independent, right? One machine's power supply dying doesn't mean the one next to it is going to die.
That's the key. This independence is what dictates the solution, which is just redundancy. You replicate the data, you replicate the components across multiple independent machines.
So if one fails, the others just pick up the load.
Right. While they're inevitable, these are, you could argue, the easiest faults to tolerate because they're not systemic.
Which brings us to the next category, software errors, which are far, far more dangerous.
We're talking about bugs.
Yep.
And software errors are so insidious because they are often systemic faults. They come from a flaw in logic, a bad assumption, a forgotten edge case.
Something that, when triggered by just the right input, can cause every single node running that software to crash at the same time.
All at once. A single, poorly handled bug can wipe out your entire redundant cluster.
And all that hardware redundancy you paid for is.
It's completely useless.
And finally, the category that always gets a sigh from engineers, human errors.
Consistently, research shows that humans are the leading cause of unexpected service outages.
And it's not necessarily, malice or incompetence.
Not at all. It's that these complex systems are just inherently brittle to human configuration choices. It's the typo in a deployment script.
The administrator running the wrong command on the production server instead of the staging one.
We've all been there. And the fix here isn't more redundant machines, it's It's process engineering. It's about designing good operational practices, creating interfaces that minimize the opportunity for mistakes.
And just having robust training and testing that keeps that human factor contained.
Right. A good design should make it almost impossible for one person making one small mistake to bring down the whole system.
Okay, let's unpack this a bit. If faults are certain, and the human element is, the number one source of failure, how do you actually gain confidence that your system can handle the chaos of production?
This brings us to a really beautiful, almost counterintuitive strategy. The incident we're trying to prevent here is the critical bug that comes from poor error handling.
Ah, okay. So you design this elaborate failure mechanism, you test it in staging, it all looks great.
And then a natural fault happens in production for the first time, and you discover a bug in the failover code itself.
Oh, that's the nightmare scenario. Your safety net was faulty all along.
Exactly. So the engineering response to this is, it's radical. You deliberately increase the rate of faults to continuously exercise the system's defenses.
This is the logic behind fault injection.
Yeah.
Famously, the Netflix Chaos Monkey.
That's the one?
Oh, I just love this idea. You literally deploy a tool that randomly and without any warning just starts killing individual processes inside your production environment. Is this just like a dramatic gesture, or is there a deep architectural reason why it's so necessary?
It's absolutely necessary because it forces a shift in your entire cultural and architectural mindset. If any process might just be killed at any second.
Then you have to design the rest of the system to handle that.
You must. The system has to immediately and transparently reroute traffic, detect the failure, start the recovery, all of it automatically. You eliminate single points of failure by making failure a constant, validated reality, not a theory.
But wait a minute. Doesn't that just introduce more operational overhead, more risk? I mean, for a small team, wouldn't constantly introducing chaos just make debugging a nightmare?
That's a valid concern, and it's most effective in certain architectures, usually microservices, where components are already designed to be loosely coupled and disposable.
So maybe not for big monolith?
The cost is high there, yes, but the value is astronomical because it all comes down to confidence. If your system can survive the Chaos Monkey on a Tuesday afternoon, you are profoundly more confident it will handle a real hardware crash at 3 a.m. on a Saturday.
You're verifying your reliability under continuous hostile fire.
Precisely.
Okay, that shifts our focus from those sudden catastrophic incidents like a total crash to something more subtle. Performance problems, specifically the challenge of latency incidents.
This is really where reliability meets scalability.
How so?
Scalability is often misunderstood. It's not just handling more requests. A better definition is maintaining good performance as the load increases. So the incident here isn't a crash, it's high variability in response times.
The system might be fast for most users, but unbearably slow for a select few.
Right. And we should define our terms here. What the user sees is response time, the total time they wait. But inside the system, there's latency.
Latency being the time a request is just waiting. Latent.
Correct. Waiting in a queue, waiting for a lock. Response time is the total duration, including network travel and all that internal latency.
Yeah.
And when we look at performance, we have to look at response time as distribution of values.
So why can't we just look at the average response time or, the median, the P50?
Because the average is incredibly deceptive. A few extremely slow requests can completely ruin the experience for some users while barely moving the average at all.
So you have to focus on the outliers.
You have to focus on the high percentiles, P95, T99, or even 99.9th percentile, the P99.9.
So that's measuring the time it takes for 999 out of every 1,000 requests to be serviced.
Exactly. These are the requests that hit the tail of the latency distribution. They're the slowest ones.
And why are these tail latencies so critical?
Two big reasons. First, there's the business impact. Amazon famously documented that just a 100 millisecond increase in response time reduces their sales by 1%.
Wow. And 100 milliseconds is barely perceptible.
But it translates to massive revenue loss at scale.
So we're not optimizing for the average user, but for the outlier experience.
Which leads to the second reason. Who are the users hitting that 99.9th percentile?
I have a guess.
They are often your most valuable customers. They're the ones with the most data in their account, the longest history, the most items in their shopping cart.
They're placing the most stress on the system because they're using it the most.
And potentially generating the most value. So making sure the system is fast for them is paramount. Overcoming latency incidents means hunting down the causes of these tail latencies, often it's queuing or weird internal pauses, and just relentlessly optimizing those high percentiles.
That's a powerful incentive to be obsessed with the outliers. Now let's tackle the third goal: maintainability and the operational incidents that come from, well, unchecked complexity.
Yeah, this incident is really about software architecture decay. As systems grow and get patched by different teams over years, they often devolve into what engineers lovingly call a big ball of mud.
Vast, poorly documented, riddled with hidden assumptions.
hmm And the incident itself manifests as slow development, right?
Exactly. Poor maintainability directly harms your reliability and your productivity. Every new developer takes longer to understand the system.
Which increases the risk they'll introduce new bugs by accidentally breaking some hidden rule they didn't know about.
The complexity itself is the operational incident.
So the goal has to be simplicity. But how do you achieve simplicity in a system that is, by its nature, incredibly complex?
Through finding excellent abstractions, that's the key.
An abstraction hides non-essential complexity. It lets you deal with a powerful concept like the idea of data without needing to worry about all the messy implementation details.
Like how that data is stored on spinning metal disks.
Exactly. Can you give us a concrete example, an abstraction we all take for granted?
Well, think about SQL. When you write a simple select from users, you are interacting with a truly brilliant abstraction.
You're asking for data based on what it is, not where it is.
Precisely. You are not telling the database, go to disk block 402, load the B-tree index, traverse the nodes, perform concurrency control.
To make sure nobody else is writing to this row at the same time and then send it back. Yeah.
So you're saying the complexity is all still there, it hasn't vanished, it's just been managed and hidden by the SQL interface.
Exactly. The database engineers dealt with the complexity of disk access, indexing, crash recovery, and all of that. So the application developer only needs to worry about, relations and queries. Overcoming operational complexity means packaging these incredibly difficult algorithms into clean, reliable abstractions that keep the system manageable.
Okay, so abstractions hold up really well when you're dealing with a single server. But the moment you move to a distributed system,
A cluster of machines communicating over a network.
the fundamental laws of physics and information just change, and that introduces entirely new classes of incidents.
And the primary reality check here is the unreliable network. When we connect independent machines in what's called a shared nothing architecture, we're dealing with an asynchronous packet network.
And what that means is that a message delay is unbounded.
Unbounded. That sounds terrifyingly ambiguous. What does that mean in practical terms for an engineer?
It means that if node A sends a request to node B and waits for a response, there is no fixed upper limit on how long it might wait.
None. The message could be sitting in a congested network switch queue.
The network cable could have been unplugged for a second.
Or node B could have just crashed and died entirely.
But from the perspective of the waiting node A, all it sees is one thing: time passing with no response.
And that's it. That is the core difficulty of distributed computing. You cannot distinguish between a node that is dead and a node that is merely slow because of a long network delay.
So we are forced to rely on a fundamentally unreliable mechanism to detect failure.
Timeouts.
Timeouts. And that creates the classic dilemma, right? If your timeout is too long, recovery is slow. If it's too short,
You risk a false positive, a very, very costly false positive. If you set a short timeout and incorrectly declare a live, slow node dead, the system might trigger a whole complex failover or leadership election that was totally unnecessary.
wasting resources, maybe causing instability.
And this happens all the time because the main source of variable packet delay isn't the physical distance, it's queuing delays.
Messages just piling up at a bottleneck switch or a loaded CPU. It's congestion.
It's rush hour traffic on the digital highway. And GCP, the standard protocol, it tries to fix this. If a packet is lost, it performs retransmissions.
But that retransmission process itself adds unpredictable delay.
Huge variable delay. It's great for reliability, but it's terrible for latency, which is why some applications have to break that guarantee.
Like video conferencing or voice over IP.
Yes. They prioritize consistent low delay over absolute reliability. They'll often switch to UDP. They're willing to trade, a dropped packet, a little flicker, or a stutter in the audio for reduced delay variability.
Because A sudden long pause is a much worse incident for a real-time conversation than a tiny glitch.
Exactly.
Okay, so the network is one source of chaos.
Yeah.
But let's talk about time itself, because it turns out your computers can't even agree on what time it is. This is the incident of unreliable clocks.
Yeah, clocks are just unstable. The quartz crystals and the chips drift constantly. So time of day clocks, the ones we look at, they have to be synchronized over the network using NTP.
But that synchronization process is where the risk comes in.
It is. If a clock drifts too far, NTP might force a sudden adjustment. Time could jump forward, or, and this is the critical one, it could jump backward.
Jumping backward. That violates causality. That's catastrophic for data integrity. What's a specific operational incident this causes?
The incident is relying on that time of day clock to measure duration, like, say, the time remaining on a lock or a lease.
Okay, so node A grants node B a 60-second lock.
But if node A's clock suddenly jumps forward 10 seconds, node A thinks the lock expired early. And if node B's clock jumps backward 10 seconds, it thinks its lock is still valid long after it should have expired.
So you could have two different clients believing they hold the exclusive lock at the same time.
Which leads to simultaneous writes and guaranteed data corruption, a devastating race condition born purely from clock drift.
So how do you mitigate this?
Well, engineers differentiate between clock types. Monotonic clocks are guaranteed never to go backward. They're perfect for measuring duration and setting timeouts, but they don't tell you the wall time.
For that, you still need the risky time of day clocks.
You do. And the most advanced solution for this really is what Google did with their spanner database.
Ah, yes. They use GPS and atomic clocks, but even that's not perfect.
Right. The key innovation is recognizing the existence of clock uncertainty. They estimate the maximum possible drift or error across all servers, and when a node commits a write, it deliberately waits out that uncertainty interval, say 10 milliseconds, before it considers the operation complete.
So it literally pauses for a tiny, defined period. Why?
Because if transaction 2 starts just 1 millisecond after transaction 1 commits, but the clocks are out of sync by 5 milliseconds, the timestamps might not reflect the true causal order. By waiting out that uncertainty interval, Spanner guarantees that transaction 2 will receive a timestamp that is numerically greater than transaction 1's.
It's a small sacrifice in latency to guarantee the integrity of time itself.
It's brilliant.
Brilliant, but clocks aren't the only thing that can just freeze unexpectedly. Let's look at the incident of process pauses and corrupted locks.
This is an incident that starts inside a single machine but can explode into a system-wide failure. A process pause is just an unbounded delay where a running program stops executing code.
And the causes are varied, right?
They are. It could be a major stop-the-world garbage collection run where the whole app halts to clean up memory. It could be heavy I/O wait times, or even a virtual machine being suspended for a migration.
So if the environment can just randomly hit pause on your process, how does that create a corruption incident?
Let's go back to the distributed locking incident. Client 1 acquires a lock on a shared file with a 30-second lease. Then Client 1 experiences a 40-second GC pause.
So its lease expires while it's frozen.
Exactly. The lock service, acting correctly, releases the lock. Client 2 sees the lock is free, acquires it, and starts writing new data to the file.
And then Client 1 wakes up.
Wakes up after its pause, completely unaware its lease expired. It continues its operation and tries to write to the storage system using its now stale authority.
Leading to clashing writes and file corruption. The lock, which was meant for safety, becomes the source of the danger.
This is what makes distributed systems so hard. These subtle, timing-based failures.
So what's the overcoming mechanism for this stale lock incident?
The standard solution is something called fencing tokens. When a client acquires a lock, the lock service doesn't just grant it. It also returns a monotonically increasing unique number, the fencing token.
Like a ticket number.
A time-stamped permission slip, basically. And every single write request that client makes to the storage system must include this token.
Okay, so how does that help?
The storage system enforces a simple rule. It will only accept a write if the fencing token presented is strictly higher than any token it has ever seen for that resource.
So in our incident, Client 1 gets token 42. It pauses, the lease expires. Client 2 comes along and gets token 43.
Right. And when Client 1 finally wakes up and tries to write with its stale token 42, the storage system just rejects it. It sees that 43 is the current authority. Corruption averted.
It breaks the dependency on synchronized clocks, making the system resilient to those unexpected pauses.
Exactly.
Okay, so we've established that relying on hardware, networks, and time is a fool's errand. Now, When we try to build high availability by replicating data across these unreliable parts, we create a whole new suite of integrity incidents, replication lag problems.
Mm-hmm. When systems use asynchronous leader-follower replication, where the leader handles writes and then updates the followers later, there is always a small, unpredictable lag.
And during that lag, different nodes in your cluster hold different values for the same piece of data.
This situation is known as eventual consistency.
And eventual consistency, while it's great for performance, can lead to some really frustrating user incidents that just violate basic expectations. The first one is reading your own writes.
This is extremely common. A user posts a comment, the write goes to the leader, they get a success message back, but then they immediately refresh the page.
And their request gets routed to a follower that hasn't received the update yet.
Right. And from the user's perspective, their comment has just vanished. The data is safe on the leader, but the perceived service has failed. It completely erodes user trust.
And the workarounds for this just show how hard it is to hide this lag.
Another really critical incident is the monotonic reads violation. Monotonicity is a simple promise. If you read a value, you should never ever read an older version of that value later on.
But with replication lag, that can happen. A user's first read hits a fast replica, and their second read hits a really lagged one.
And suddenly the data appears to revert to an older state. It's incredibly disorienting. It's like history is rewinding in front of your eyes.
And the third one violates causality itself. The consistent prefix reads violation.
Yeah, this one is tricky. It means that if two writes happen in sequence write 1, then write 2 or reader might see write 2 before they see write 1.
Like seeing the answer to a question on a forum before you see the question itself.
Exactly. It breaks the logical sequence of events. Overcoming all these anomalies requires very careful management of causality, making sure read requests are always served by a node that has a logically consistent view of history.
Okay, so that's data moving between nodes.
Yeah.
We also talk about concurrency anomalies. What happens when multiple transactions are trying to change the database at the same time?
Right, and this requires us to understand the slippery concept of a transaction. Transactions are supposed to be atomic, all or nothing, which is great for error handling.
But the word consistency itself is used in like 4 different really confusing ways.
Yes. There's ACID consistency, which is about your application's own rules. There's isolation, which is about how concurrent transactions interfere with each other. There's linearizability, which is a guarantee of recency. And then there's eventual consistency, which we just talked about.
When engineers talk about anomalies, they're usually focused on isolation.
That's right. So let's break down the most common isolation anomalies that lead to data corruption. First up, the dirty read.
A dirty read is when transaction A reads uncommitted data written by transaction B.
Right. And if transaction B then aborts, for some reason the network drops, whatever transaction A has now based its logic on data that never actually existed in the database.
It was provisional data that just vanished.
Leaving transaction A in a corrupted state.
Okay, that seems like a fairly easy one to fix just by only reading committed data.
Mm-hmm.
What's next? Read skew.
Read skew is when a transaction observes the database in a state that is logically inconsistent with its own rules. Imagine a bank transfer of $100 from account A, which has $500, to account B, which also has $500.
The rule, the invariant, is that the total balance must always be $1,000.
Correct. But during the transfer, if a separate monitoring transaction checks the balances, it might see account A has been debited, so it has $400.
But account B hasn't been credited yet, so it still has $500.
So the monitor sees a total of $900. It's a temporary state, but it means the reading transaction is viewing an impossible version of reality. Its view is skewed.
Okay, now for the classic one, the lost update. This feels critical because it's a silent failure.
It's so dangerous. The lost update happens when 2 transactions do a read-modify-write cycle at the same time. Think of 2 people clicking an increment counter button.
Both read the current value, say 10.
Both calculate the new value, 11, in their own memory. Then the one that writes last just overwrites the first writer's result.
So you had 2 increments, but the counter only went up by 1. The system silently lost a whole update.
And the database has to intervene here. The usual mechanisms are explicit locking, like select for update, which makes one transaction wait. Or you can use atomic operations like compare and set.
Where the write only succeeds if the value hasn't changed since you first read it.
Exactly. Which brings us to the most complex anomaly, the one that requires the strongest protection, write skew.
This one is so subtle because it involves 2 transactions writing to completely different things, but still violating an application rule.
Let's use the doctor on call example. The rule is, at least one doctor must always be on call. We start with two doctors, Alice and Bob, both on call.
Okay.
Alice starts a transaction. She leads the list, sees two doctors are on call, so her premise holds. She decides to go off call and writes an update to her own record.
Concurrently, Bob does the same thing. He reads the list, sees two doctors, premise holds. He decides to go off call and writes an update to his record.
Since they updated different rows, neither write conflicts directly. Both transactions commit successfully.
But the end result is that 0 doctors are on call. The application invariant is violated.
The premise they both acted on, there is at least one other doctor, became invalid the moment the other transaction committed. That's why right skew is so dangerous.
So when we look at overcoming anomalies, the engineering world uses different isolation levels. Snapshot isolation is a big one.
Snapshot isolation is a huge leap forward. It guarantees that your transaction operates on a consistent snapshot of the database taken the moment it began. This beautifully fixes read skew and dirty reads.
Because the transaction never sees those weird, temporary conflicting states.
Right. Though we should note the naming is confusing. PostgreSQL and MySQL call their implementation repeatable read, which is a different concept historically.
But even snapshot isolation isn't enough for that right skew incident, is it?
It is not. SI protects you when you read an inconsistent value, but it doesn't protect you when you base a decision on a premise that another transaction invalidates. The only isolation level that protects against all of these anomalies, including right skew, is serializability.
The gold standard. It guarantees that the concurrent execution gives you the exact same result as if all the transactions had just run one after another in some sequence.
And it is absolutely necessary for maintaining those critical application level rules like uniqueness constraints. The engineering cost is high, but the cost of data corruption from a right skew incident is often much, much higher.
Okay, we've now established that managing consistency inside one database is hard enough. But the ultimate challenge comes when we need multiple independent nodes to agree on something fundamental.
Like who won the race, or who is the current leader. This introduces the deep theoretical incident, the impossibility of consensus.
This takes us to the famous FLP result, named for Fisher, Lynch, and Patterson. It's a cornerstone of distributed computing theory.
And it states that in a purely asynchronous system, where messages can be delayed arbitrarily and nodes can crash, no deterministic algorithm can ever guarantee that consensus will always be reached in a finite amount of time.
You can't have both safety, everyone agrees on the same thing, and liveness. The system actually makes a decision at the same time.
It feels like the universe telling engineers, you can't have it all. So if consensus is theoretically impossible, how do we build reliable systems?
We have to find pragmatic ways to get around the theory, and there are two main workarounds.
First, you can introduce randomness into the algorithm. But much more commonly, you allow the algorithm to use timeouts and these unreliable failure detectors.
So we accept that the timeout might occasionally be wrong, but that acceptance is what allows the algorithm to eventually terminate and make a decision.
Exactly. We use the unreliable tool of time because it lets the system make progress. And this necessity is why trying to get ACID atomicity across multiple nodes is so fragile, which leads to the infamous atomic commit incident.
Usually attempted with the two-phase commit protocol, or 2PC.
Right. 2PC aims to ensure that if a transaction spans several databases, either all of them commit or all of them abort.
So walk us through where this process catastrophically fails.
Okay, 2PC has two phases. In phase 1, a coordinator asks all the participants to prepare and vote yes or no. Once a participant votes yes, they've made a binding promise. They have to wait for the final decision.
And phase 2 is the coordinator collecting the votes and sending out the global commit or abort.
Yes, the incident, the catastrophic failure, happens right in that window between the two phases. It's the coordinator crash.
If the coordinator crashes after a participant has voted yes, the point of no return, but before it sends the final decision,
The participant is completely stuck.
what state is it in?
It's in an in-doubt or uncertain state. Because it promised to commit, if told to, it has to hold all the database locks it acquired for that transaction. But since the coordinator is down, it's waiting indefinitely.
And those indefinitely held locks block all other reads and writes on that data across the entire system.
So 2PC turns a single coordinator failure into a denial of service incident across multiple other systems. It amplifies the failure instead of containing it.
Which is why you just don't see it used in modern web-scale systems.
It has exceptionally poor fault tolerance, which brings us to the modern solution, the one that really does conquer the impossibility of consensus. Fault-tolerant consensus algorithms like Paxos and, more recently, raft.
These are designed precisely to avoid that 2PC incident.
They are. They rely on the power of a majority, a quorum, to assure both termination and safety. If you have 5 no's, as long as 3 of them are working correctly, the system can guarantee it will make progress and reach agreement.
It can tolerate failures of up to half the nodes.
Right, so the system might stop processing new requests if too many nodes fail, but the data integrity is never, ever compromised. Safety is always guaranteed. It sacrifices liveness, it might pause, but it never sacrifices safety.
And the key abstraction that these incredibly complex algorithms provide is something called total order broadcast.
Total order broadcast is the holy grail. It ensures that all the functioning nodes agree on the same exact sequence and ordering of all operations.
So if every node applies the operations in the same order, client A's right always comes before client B's right, you can build really reliable systems on top.
You can. You can implement linearizable atomic operations, uniqueness constraints, distributed locks, all without the fragility of 2PC. It provides a foundation of a perfect shared history.
And thankfully, engineers don't have to implement Raft from scratch every time they need this.
No, thankfully. They typically outsource this incredibly complex work to tools like Zookeeper or etc.
They abstract away the consensus complexity.
Right. They run on a small, dedicated set of nodes and just provide that linearizable atomic coordination layer for everyone else to use.
Right. Moving from these low-level coordination problems to a higher-level architectural design, we find an incident that leads to silent, permanent data corruption across organizational boundaries. The dual writes and permanent inconsistency incident.
This is a massive integrity failure, and it's really common in service-oriented architectures. An application needs to update information in 2 completely separate, different storage systems.
Like updating a user record in the main database and updating the corresponding document in a search index.
Exactly, and the application tries to handle these 2 writes independently.
And the moment those writes are independent, the system is fundamentally broken, right?
Yes, because there's no atomic guarantee that both will succeed. If the database write works, but the search index write fails, the 2 systems are now permanently out of sync.
And if 2 clients submit updates at the same time, the database and the search index might process them in different orders,
leading to completely inconsistent, non-linearizable results across the whole system.
So the solution is to reimpose that total order broadcast principle at a global level. You have to ensure there is one, and only one, single system of record that dictates the definitive order of all writes.
Precisely. The application only ever writes to that one source of truth, the main database, or maybe an event log, and all other systems, the cache, the search index, the analytics dashboard, they all become derived outputs of that single ordered stream.
What are the main mechanisms we use to derive those secondary systems?
One method is change data capture, or CDC. That involves treating the database's internal commit log, its replication stream, as a source of events that other services can just subscribe to.
So every update, insert, or delete in the primary database gets streamed out.
Right. The other major method is event sourcing, where the log of immutable user actions is the primary system of record, and the current state is just rebuilt by replaying that log.
And that concept of building state from an immutable log brings us to one of the most powerful tools for incident recovery.
The advantage of immutability in recovery.
Yeah, talk about that.
Think about it like an accountant. An accountant never erases a mistake. They enter a new corrective transaction.
Right.
So if your mutable database gets corrupted because of a software bug you just deployed, a major incident fixing it is complex and super high risk. You might lose critical history while you're trying to patch the broken state.
But with an immutable log, the source data is always preserved.
Yes. If your source of truth is an immutable log of events, recovery becomes drastically simpler. You just fix the bug in your derivation code, and then you reprocess the entire immutable history through the newly fixed code.
And the system just rebuilds the correct state from scratch,
compensating for the mistake without losing any of the original transaction history. It makes recovery from software errors so much more robust.
That's a huge win for maintainability. Now, in this world of asynchronous data flow, we have to formally address this necessary trade-off: timeliness versus integrity.
Integrity is the core property. It's the absence of corruption, the correctness of the data. A violation here is permanent and catastrophic.
And timeliness is how quickly the data updates and becomes visible. It's related to low latency and linearizability.
And coordinating for perfect, instantaneous timeliness costs a fortune in performance and fault tolerance.
Right.
So these asynchronous data flow systems using event streams, they choose to decouple these concerns. They sacrifice strict timeliness. They accept that the search index might lag a few seconds behind the database, but they use powerful ordering mechanisms to maintain incredibly strong integrity guarantees.
The derived data will be correct even if it arrives a moment later.
And that strategic sacrifice leads us to the final brilliant architectural pattern. Leveraging loose constraints and coordination avoiding systems, it's all about asking, when is coordination really necessary?
So strict synchronous coordination, the kind you need for serializability or 2PC, is only necessary when a business rule must be instantly enforced with absolute timeliness.
Right, like making sure two people don't simultaneously buy the very last item in inventory. That requires expensive consensus.
But you'd argue that many real-world constraints don't actually need that instant high-cost enforcement.
That's right. Many business rules, like preventing a flight from being overbooked or a bank account from being overdrawn, can actually allow for temporary violations. You can address the incident later.
Using a compensating transaction and often an apology.
Or a fee. So if a system briefly overbooks a flight because synchronous coordination was too slow, you accept that temporary incident and you fix it later by moving a passenger and giving them compensation.
And by accepting that temporary loss of strict timeliness, you get to avoid all the complexity, the performance penalties, and the fragile fault tolerance that comes with that synchronous coordination.
It allows you to build systems that are far more robust and scalable, achieving high integrity over the long run by avoiding the very coordination mechanisms that often become the biggest source of incidents in the first place.
We have completed a really comprehensive deep dive today. We've gone from the isolated, random death of a physical hard drive all the way up to the theoretical impossibility of achieving consensus across a global network. And we see that reliable systems are built not by wishing away uncertainty, but by embracing failure and confronting that unreliable reality head on.
Using tools like Chaos Monkey, fencing tokens, and immutable event logs, the foundational lesson for the learner, I think, is that every engineering success we discussed, from mitigating tail latency to guaranteeing serializability, is a carefully crafted response to a specific known incident that engineers have observed in the wild.
We build reliability one defense at a time.
That's it.
And as the systems we build get bigger and handle more and more of our lives, the focus on integrity has to extend beyond just the technical data layer. If we accept that we can't fully trust every component to be bug-free,
then we have to look at the larger scope of our system's correctness. We talked about ensuring data integrity through strong consistency models and immutability. But the data we collect and analyze carries immense risk. The very act of tracking and aggregating user activity creates these vast, complex, derived data sets that are often opaque.
beyond the full comprehension of the people they describe.
Exactly. So if corruption is possible, if a software bug can lead to data loss or integrity failure, then we need built-in mechanisms to catch these systemic problems.
Which brings us to our final provocative question for you, the learner, and it's this. How do we engineer auditability and integrity, checking that end-to-end argument for correctness into the very design of our data systems?
Not just to prevent a lost update in a database, but to ensure the entire system remains accountable and auditable over its entire lifespan.
That is the ultimate design challenge. Building systems that are not only resilient, but also verifiable.
A profound thought to end on, connecting that technical struggle for consistency to the societal need for accountability.
Thank you for joining us on the Deep Dive.
Dive responsibly.